We have G and F sigma algebras, G a subsigma algebra of F, and X and Y random variables which have finite expectation. That means that is they're in L1. We're going to prove some facts about conditional expectation, just using the definition of conditional expectation, which is the unique random variable satisfying a certain integral equation that we will have seen in the lectures. So to start off, we're going to prove linearity. Let lambda be a real number, and z equals lambda multiplied by the expectation of x given g plus the expectation of y given g. We're going to prove that z is the conditional expectation of lambda x plus y given g, and this is a really classic way of proving things for the conditional expectation. We're going to do it by using the uniqueness property that the conditional expectation should be the uniquely g measurable random variable which satisfies this particular integral equation, which we can also write as an equation of expectations that we'll see just in a moment. So first we'll note that as a linear combination of, that should be a g, of g measurable functions or random variables, z is itself g measurable. This measurability feels like a technicality, but it is really crucially important for the definition of the conditional expectation and shouldn't be forgotten. Second, now what we want to show is that for all a contained in G, the expectation of z multiplied by the indicator of a is equal to the expectation of lambda x plus y multiplied by the indicator of a. If this is true, then by uniqueness, z will be almost surely equal to the conditional expectation. Well, let's do that. Expectation of z multiplied by indicator of a is equal to, just first, by linearity of expectation, nothing more, is equal to the expectation. Lambda, I've already taken out, multiplied well, indicator of a times, where have I written z? Here. Expectation x given g. Actually, I'm going to first write that with the lambda inside, and then I'm going to split everything out. This is just the definition of z, nothing more. Now, linearity of expectation allows me to separate out these expectations. So we have 1 indicator of a multiplied by expectation of x given g, just a random variable, multiplied by lambda, plus expectation indicator a multiplied by expectation of y given g. Just linearity of expectation and nothing else. Now, we know by the definition of these conditional expectations, here and here, that this equation on the left, well, that is equal to lambda times the expectation of indicator a times x. That's the definition of conditional expectation. It must be true. Same on the right hand side. Indicator a multiplied by y. That's definition of conditional expectation. Now what remains is to use again linearity of expectation to bring these things all back in. Expectation, indicator a, lambda, x plus y. And as was mentioned at the start, that's exactly what we had to show. From this, because this is true, because z is a random variable that satisfies this for all A in our sigma algebra, that should be G, and Z is G measurable, it follows that Z is equal to the conditional expectation of lambda x plus y given G, almost surely. This trick of proving something is a conditional expectation by just using the properties of the definition is a classic trick that is extremely useful for proving things about conditional expectation. Okay, second, part B. Suppose x is greater than or equal y. We're going to prove that the conditional expectation of x is greater than or equal to the conditional expectation of y. This is called monotonicity. Again, it's something that you would expect, but still worth proving. Okay, let's let A be the event. Sorry, notation doesn't look good. I'm saying define it to be the event. That expectation of x given G is less than the expectation of y given G. Of course, these guys are random variables, so we want to show that this A has probability measure 0. Right? What I actually mean here is so A to be a subset of omega. This is, of course, all omega in omega, such that this is true. It's important to note that since both of these conditional expectations are G measurable, that's in the definition of conditional expectation, it follows that A is a subset of G, an element of G. We know already that it's an element of F, right? Certainly because both these guys are F measurable random variables, but they're also G measurable because they're conditional expectations. So A is an element of G. From the definition of A, we see that if A has positive probability measure, that what we want to show is not possible, then it follows that the expectation of x given G minus the expectation of y given G, both random variables, multiplied by the indicator of A is less than 0. What's happening here? Well, this is just a random variable that on event A is less than 0, right? This expectation, we're just integrating this particular random variable multiplied by this random variable against this probability measure. Well, this thing is negative when this thing is equal to 1 on A, so I could just remove that and say we're integrating over A. And if then P has a positive measure of this A, then this is less than 0. Right? Otherwise, if P had 0 measure, then this integral could, of course, equal 0. So, in addition to this, from the definition of conditional expectation, also using linearity from A, and the fact that x is greater than or equal y, using all of these three, it follows that the expectation of this thing that we just looked at, the expectation of G, x given G minus y given G, multiplied by indicator of A. Well, linearity allows us to combine these things together, right? Expectation of x minus y given G, multiplied by the indicator of A. I don't really need those second brackets, but I probably can't remove them without deleting everything. Let's try. There we go. That's just linearity. And by definition of conditional expectation, as we said, because A is in G, this is equal to expectation of x minus y, given multiplied by indicator A. That's just definition of conditional expectation. And since x is greater than or equal y, not even almost surely, but just for every omega, but it could also be almost surely here, this is greater than or equal 0. Right? We have a non-negative random variable multiplied by a non-negative random variable, then of course the expectation is not negative. But so, since we know that the expectation of this is greater than or equal 0, we can see from what we calculated above that it cannot be possible that probability of A is greater than 0. Right? We can use the contrapositive. It therefore follows that the expectation, that the probability of A is equal to 0. Can't be greater than 0, has to be equal. And that's what we had to prove, right? A is exactly this event that we wanted to show has probability 0. And it follows that expectation of x given G is greater than or equal to expectation of y given G, almost surely. Finally, part C. We want to show that if G is independent from the sigma algebra generated by x, then the expectation of x given G is just the expectation of x. So, suppose that sigma x and G are independent. This implies that for any set A in the sigma algebra G, random variables x and indicator A are independent. Independent, I can spell that. So of course independence of sigma algebras is not exactly the same concept as independence of random variables, but this is the connection between them, and we can use the second more easily. Let's let Z denote the expectation of x. Since Z is not random, right, it's just a single number. It's not a random variable, although if it is, it's like a trivial one. Since Z is, there we go, hang on. Since Z is not random, it is trivially G measurable. A random variable is measurable against the sigma algebra if the pullback of sets in the Borel sigma algebra are contained in that sigma algebra. And it's something that you can prove for yourself that this is true, but basically the pullbacks of Z will be either the empty set or omega. Those are the only two possible pullbacks of a non-random number. So since they are contained in any sigma algebra, it follows that a deterministic number is measurable against any sigma algebra. So further, for any A in G, we can use this independence that we just mentioned to see that the expectation of Z multiplied by indicator of A equals expectation of X, but with the indicator of A inside the expectation. That is independence, equals the expectation of X times the indicator of A. So Z is G measurable and satisfies this equality. And again, uniqueness of the conditional expectation, that incredibly valuable property, gives that Z is equal to the expectation of X given G. And that's what we wanted to show, that the expectation of x given g is equal to the expectation of x, which is what we had how we define z. So the exercise has been proven.